Hello, everyone. Today we'll be diving into one of the most fundamental concepts in engineering mechanics, beams. As we explore this topic, you'll discover how these essential structural elements form the backbone of modern construction and engineering. Let's start by understanding what exactly a beam is. Imagine a bridge spanning across a river. At its core, it's supported by beams. A beam is a horizontal structural member that's specifically designed to handle forces coming from different directions. Think of it as nature's way of distributing weight, similar to how a tree branch supports its leaves and fruits. When we load a beam, it experiences three main types of stresses: bending, shear, and torsional stresses. The beauty of beams lies in their ability to transfer loads from above to vertical supports, much like how your shoulders help distribute the weight of a backpack. They're typically long and slender and can be made from various materials like steel, wood, or reinforced concrete, each chosen based on specific requirements of the structure. Now, let's explore the diverse family of beams. Just as we have different types of tools for different jobs, we have various types of beams designed for specific purposes. These classifications are based on three main factors: how they're supported, their shape, and the type of loads they carry. Think of it as organizing your toolbox. Each beam type has its special place and purpose. Understanding these classifications is crucial because it helps us choose the right beam for the right job, just like you wouldn't use a hammer to tighten a screw. Let's focus on our first beam type, the simply supported beam. Imagine placing a wooden plank across two chairs. That's essentially a simply supported beam. These beams are supported at both ends and are free to rotate, much like a seesaw in a playground. What makes them special is their simplicity and analysis. They only have vertical reactions at their supports. When we load these beams, whether with a point load, like someone standing in the middle, or a uniform load, like books spread across the plank, they respond in predictable ways. This predictability makes them extremely popular in construction and a perfect starting point for understanding beam behavior. Moving on to cantilever beams, these are fascinating structures. Imagine your arm extending straight out while holding a book. That's essentially a cantilever beam in action. These beams are fixed at one end and free at the other, commonly seen in balconies and traffic signals. The most interesting aspect of cantilever beams is how they handle forces. They experience maximum bending moment at the fixed end and maximum deflection at the free end. It's like holding a fishing rod. You feel the most strain where your hands grip the rod, while the tip shows the most movement. Picture a gymnast's horizontal bar, but firmly welded at both ends. That's similar to a fixed beam. These beams are special because they're rigidly fixed at both ends, preventing any rotation or movement at the supports. This makes them incredibly strong and stable, perfect for high-strength structures and frames. When we analyze fixed beams, things get a bit more complex because of something called fixed end moments. Think of it like trying to twist a metal rod that's welded at both ends. It's much harder to move. This rigidity is both a blessing and a curse. While it reduces deflection, meaning less sagging, it makes our calculations more challenging. But don't worry, we'll learn to master these calculations step by step. Let's talk about continuous beams. Imagine a long highway bridge stretching across multiple pillars. That's a continuous beam. These beams are like the marathon runners of the beam world, extending over multiple supports. What makes them special? Well, they're incredibly efficient at handling loads. By spreading the load across multiple supports, they reduce the maximum bending moments compared to simple beams. It's like distributing the weight of your shopping bags across both hands instead of carrying everything in one hand. However, when analyzing these beams, we need to consider something called compatibility conditions, essentially making sure that the beam behaves as one continuous unit rather than separate pieces. Now, let's examine overhanging beams. Think of a diving board at a swimming pool. These beams have a portion that extends beyond their support points. They're commonly used in canopies and architectural features where we need that extra reach. The fascinating part about overhanging beams is that they combine properties of both simply supported beams and cantilevers. The overhanging portion acts like a cantilever, while the supported portion behaves like a simply supported beam. It's like having the best of both worlds in one structural element. Let's discuss the types of loads acting on beams. Beams are subject to various loads that induce stresses, moments, and deflections, which require precise analysis. A point load, also known as a concentrated load, acts at a specific point on the beam, such as a column supporting a beam at a single point. This type of load produces sharp changes in shear force and generates a bending moment curve. In contrast, a uniformly distributed load, UDL, is spread evenly across a section of the beam, like the weight of a floor slab distributed across a beam. UDLs create parabolic bending moment curves, and shear force varies linearly along the beam. Understanding these load types is crucial for structural analysis and design. Uniformly varying load, UVL, and moment, couple, are two additional types of loads acting on beams. A uniformly varying load, UVL, has an intensity that varies linearly along the beam's length, such as water pressure acting on a submerged beam. Analyzing this load requires integration to calculate bending moments and shear forces accurately. On the other hand, a moment couple is a pure rotational force applied at a point, like torque applied at the ends of a shaft. This type of load directly influences the beam's bending without affecting shear. Let's delve into the fascinating world of beam reactions. To understand this concept, imagine a beam as a perfectly balanced seesaw. For any beam to remain stable, all forces acting on it must be in perfect equilibrium. We use three fundamental equations to ensure this balance. The sum of horizontal forces must be zero, the sum of vertical forces must be zero, and the sum of all moments about any point must be zero. These aren't just mathematical equations, they're the fundamental rules that keep our structure standing. When calculating reactions, we can use various methods like static equilibrium analysis or the section method, each offering unique insights into how our beam behaves under load. In this practical application slide, let's consider a simply supported beam carrying a uniform distributed load, UDL. Here's a beautiful simplification. When we have a symmetric beam with a uniform load, the reactions at both supports are equal. The equation RA equals RB equals WL by 2 tells us that each support carries half the total load, where W is the load per unit length and L is the beam's length. Think of it like two friends sharing the weight of a long box. If they're standing at equal distances from the ends and the box has uniform weight, they'll each carry exactly half the load. This principle makes initial calculations much more manageable and provides a solid foundation for more complex analyses. The space diagram is like the blueprint of our beam analysis. It's more than just a drawing. It's a visual story that tells us everything we need to know about our beam setup. Just as a chef needs to lay out all ingredients before cooking, we need to clearly represent all elements of our beam problem. This includes showing the beam's exact length, identifying support types, whether they're fixed, pinned, or on rollers, and marking all loads acting on the beam. A well-drawn space diagram is like having a clear roadmap. It helps prevent errors and makes our analysis much more straightforward. Remember, in engineering, clarity in representation leads to accuracy in calculation. Now, let's explore the different ways we can support our beams. We have three main types of supports, each with its own unique properties. First, there's the pin support, which acts like a door hinge. It can rotate but won't move up, down, or sideways. Then we have roller supports. Imagine a beam sitting on marbles. It can move horizontally, but not vertically. Finally, we have fixed supports, which are like firmly cementing the beam end into a wall, no movement or rotation allowed. Each support type affects how our beam behaves under load and determines what types of reactions we'll need to calculate. Understanding these support types is crucial because they directly influence how forces are transmitted through our structure. Let's explore the effect of couples on beam behavior. A couple is a type of load that creates pure rotation without translation, similar to twisting the cap of a water bottle. In beams, couples generate pure bending moments without shear forces, causing the beam to curve without sliding. When analyzing such beams, we calculate the support reactions due to the applied moments. For example, a simply supported beam with a central couple will rotate around that point, with supports developing reactions to maintain equilibrium. The bending moment diagram shows how the rotational effect spreads through the beam. Understanding couples is essential for real-world applications like machinery torque and wind-induced twisting on tall buildings. In the real world, beams are everywhere, holding up floors and roofs, supporting bridges, and integral to mechanical systems like cranes and aircraft wings. Beam analysis ensures these structures are safe, efficient, and economical. It's crucial for designing transportation infrastructure, shopping malls, stadiums, and skyscrapers, making our built environment strong and functional. We have reached the end of this video today. Thank you for watching, and don't forget to like and subscribe for more tutorials on other exciting topics.